So I think this will work out. Online, right? Yeah. So, welcome everybody. It's a full house tonight for our. I don't know which Twed of the spring 2018 this is, because we've been having a lot of RPI, our users groups, and idea talks or idea/Twed talks this term. But this is an honest to goodness Twed talk with a deep carbon observatory focus, which is excellent. We haven't heard from DCO people for a while up here. A couple logistics notes. We are, as usual, we are streaming live to the interweb, and we're recording this. Feel free to ask questions. Yeah. But just keep in mind that we are streaming. I'm usually the worst offender as far as that goes. We're getting now, we've turned the corner. The All-Star game has happened, and we're getting closer to the end of the term. So I'll start soliciting you to sign up for end of the term Twed lightning talks, and I'll beat on you ceaselessly until we fill up that schedule. So please do sign up. The link is in the emails that get sent out. Thank you, FeiFei, for doing the talk tonight. I'll let FeiFei introduce the topic.
Hello, everyone. My name is FeiFei Pan. I am a second-year computer science PhD in Professor Peter Fox's group. And today I'm going to present one of the projects I'm working on. It's a derivative, kind of like from both Deep Carbon Observatory and the NT project. So it is the data science implications in diamond formation and Craton evolution. Okay, first of all, it's the agenda. First of all, I'm going to introduce why we're doing the projects, and then some project descriptions. After that, there's two parts. The first part, including data rescue and data processing. It's a part that we get the data ready for the second part, which the big chunk of it is the machine learning implementations. Also, we plan to do visualizations in different formats. And then at the last, I will describe the future work. First of all, the project is funded by Deep Carbon Observatory. For short, it's called DCO. It is almost 10-year-long global multidisciplinary project. Involves scientists, researchers from all over the world, and it studies the deep Earth, especially the carbon. So it studies how much carbon are there on the Earth, where they're from, which form it takes, also how it evolves throughout the years. So there's 4 different research groups. I believe this project belongs to the extreme physics and chemistry group, because I am currently working with Found. Found's PhD work belongs to this research community. Yeah, here's the introduction. So why we want to study diamonds. So talking about diamonds, the definition is a solid form of carbon with the diamond cubic crystal structure as listed there. And generally for the public, when we think about diamond, it's like shiny, kind of like small, expensive, solid material that goes on jewelries. But there's also a lot of diamonds that are not precious, they're not expensive at all. Basically, they're our study objects. The ones has a lot of inclusions in it, either flood inclusion or mineral inclusions. So these ones are the reason why we want to, the inclusions of the part we want to study. So why we want to study inclusion? The ultimate goal is we want to study the very deep part of the Earth, which we cannot get into there. But diamonds are like the messengers from deep Earth that bring all the minerals and inclusions and liquid in it to the ground. So inclusions in diamonds are basically the only direct sample we can get from deep Earth. And the study is very important because it can help us to understand the Earth's history, the present, and also the future. As I said before, the project is divided into 2 parts. The first part is the data rescue and data processing cleaning part. So in this part, we plan to rescue all the data from publications, including journal papers, PhD, master thesis, and all kinds of field data thing that's all the tables from the publications. And then we get the data ready into a complete and easy accessible data set or database. We haven't decided on that yet. So, and that is used in the second part, which we use the data to answer scientific questions in geoscience research domains. So we construct machine learning models, we do data analysis, data visualizations to make sense of the data. So here's the 4 components of the projects, including data rescue, data cleaning and processing, data analysis, and data visualizations. So I will go into detail in the following slides. The first part is the data rescue. Here's the workflow. So the very beginning of this project, we have a review. It's a publication from Professor Thomas Stachel. And in this review, he made conclusions and of all the papers published before 2008. And in the appendix, he has a full list of all the papers he mentioned in his review. So the first step is we rescue all the documents he mentioned in the list. So all the lists are basically in PDF format. And the major part of this data rescue is we want to convert all the tables in the PDFs into either Excel file or CSV files. For the data rescue, the biggest challenge we face is a lot of papers are not actually in machine readable format. They are in PDFs, but they are scanned from either journals, books, or they are type machine document, especially the ones before 2000, especially the one before 1980s. There are 2 software. Well, there's actually two major category of softwares we use. The first one is called PDF Figure 2.0. It is it can extract figures and captions and tables and also section titles from PDFs. It is written in Scala, and the results are saved in image format. And then we have all the table image, and we put the image into an online OCR tools, which can convert it into the tables, which preserve better format compared using PDFs directly. So in the data rescue outcome, I pretty much is focused on the ones before 2008. Is pretty much from the list of the review, and use some keyword search online to try to gather all the papers after 2008 and get all the tables out. So here is the data processing, which is our ongoing work, is to integrate all data into a maintained database, and we want to store the data into DCO data portal. So as I said before, DCO is a large project that a lot of people are involved. So they have a data portal that store all the information on either researchers, scientists, or publications, and also the data they gather from the fields. So our goal is to have our data set ready, put into the data portal, to make it accessible to the DCO community, whoever with the DCO portal ID, so they can register online or something like that. So also we want to make the data ready to query for and ready for data analysis for using in machine learning models for visualizations. So here's the challenge. There's a lot of human efforts needed in this part. Either cleaning, dealing with some missing data, put it into, put all the small tables into all the small pieces into a huge Excel file that contain all the documents in a clear format. So the first part is Found as a domain expert, he needs to work on to pick which columns goes into the Excel file, including all the minerals. Do we need the temperature, pressure, or do we need the location, and do we need trace elements, all these decisions. And then we need to have our data put into the giant spreadsheet. So as I said, a lot of human efforts is very time consuming. And if you know anyone who's interested in this project, undergrads, masters, you can let them contact me or Fang. Fang's always going to be on the second floor on weekdays. So the data description. So before we go into the big data set, which we don't have it ready now, we want to take a baby step. So we want to look at a smaller data set and see what we can do from that data set. The data set is basically the ones on Professor Sobolov's work, and it's about 570-something rows. Has 32 features, including chemical compositions, mineral label, Craton label, paragenesis. I think that's pretty much important information. In this project, till now, we have 3 use cases. The first one is we want to do the clustering based on the mineral compositions and compare the clusters we got with the ground truths and then see if they agree with each other. Also, we did a principal component analysis that see which chemical components affect the clustering the most. For the last part, we did a classification on chemical compositions versus mineral tab and Craton tab and see if there's ongoing relationship. So machine learning is the second part of the project, is aimed to answer well-defined scientific questions that maybe if we don't use machine learning, it's going to take too long or unable to answer. So as I said before, we have 3 experiments. The first one is the clustering using k-means and PAM, the PCA, the principal component analysis, and the final one is the classification. We used 4 different algorithms and different kernels for the supported vector machine. So here's the first part. I'm not going to go into the detail of the mathematical things, but the reason why we want to do it is we want to see if we ignore all the labels, how many clusters we can get from all the minerals, and does it agree with what we have as the labels. In this part, we use 2 algorithms. One is PAM and the other is k-means clusters. And we calculate the COLX score to see what number of cluster is the best for our data set. For the results, the COLX score, if anyone who don't know it, is to calculate this dissimilarity among clusters. So when the score is higher, it means we get better clusters. We evaluated class number from 2 to 20, and then 27, 30, 40, until 60. The best we got is at number 13. For the cluster analysis, for the conclusions that we found out that our clusters are mostly agree with the ground truths we have, the mineral labels we have. So we will say that it's closely related, and there are some minerals that be divided into 2 different clusters. For example, the garnet. And also there's different minerals are categorized into the same clusters. There are 3 examples. From now, we see that Craton, paragenesis, and chemical compositions are not considered strongly correlated. But in the classification, we have some new findings. I will go into detail then. The second part is we performed a principal component analysis, which is we aim to find out which minerals affect, which chemical composition affect the clustering most. In this part, this part is majorly used for the visualization in the last of this presentation, and we found 3 important factors: magnesium, silicon, and CR2O3. The last one is actually, well, the first 2 is actually very commonly existed in the inclusions. So we expected them to be one of the major factors, but the middle ones are new and think there's a lot of interesting things can be discovered associated with that. So clusters, the center clusters, especially the garnet, are affected by many small factors, small components, and the outlier clusters are basically affected by the closest factors associated with it. The final part is the classification. So we want to use, we want to predict mineral and Craton using chemical compositions. We use 4 different algorithms, and we want to discover if there's any relationship between compositions, mineral, the combination of chemical composition and mineral, as long as with Craton. So here's the results. First column, predict task 1, is the chemical composition with relationship with the mineral label. So as we can see that if we know the chemical composition, we can almost certain about the mineral label it belongs to. So the second task is using chemical composition to predict Craton. Before, we thought it's definitely not correlated. So the results from near centroid and naive Bayes is what we expected. But by using SVM, I think it's the RBF kernel, we found out that the correlation is about 70% average. So that means there might be something going on underneath. So Fang is making sense of the numerical numbers because he is a domain expert. So and for the experiment, of course, we will run 5-fold cross-validation and other calculations. So here's a visualization. On the left part is the original data plotting 2D based on the 2 principal components, and different colors refers to different minerals. On the right side is the COA score trends after repeating different numbers of clusters. So as we can see, at number of 13, it reaches max. So for both methods, we use cluster number 13. This is the clustering results after we run k-means and PAM. So as we can see, the clustering is a little different between them, and with the PCA on it, we can see there's 3 major, the longest vectors, they are the 3 major components, and in the center of the plot, there's many small ones that you can see it when I zoom in the next slides. So here's the one from k-means. After zooming in the center part, you can see there's a lot of small ones. So garnet, the cluster of garnet is affected by all these small components. And this is the same thing on same thing on PAM. That I think this is the garnet. The garnet has all these factors affected it. So here's the future work. We have a lot of work need to be done on the mineral inclusion in diamonds. We want to perform more comprehensive cluster analysis on the whole data set when it is ready. We want to understand current findings, which is what Fang is doing right now. He's making sense of all the results. And we want to form better scientific questions that can be answered by machine learning methods. Also, we want to build and tune more machine learning models. Now we have classification. We probably want to do regressions if we get more information like temperature, pressures. Also, we can run neural network. Now the data set is small. We probably want to reduce the number of layers. But when we got the large one, we can also try fancier machine learning models like deep neural network, things like that. The visualization is for the visualization, we want to do network analysis using these 3 visualization. Also, currently we are thinking about applying VR techniques into introducing it into the DCO community, and we can probably also use that as well. The next step is the flood inclusion in diamonds. Actually, there is a relatively complete data set on flood inclusion already. So we probably just want to do a little similar data analysis and visualization, and then we can do a mineral and flood co-analysis for the inclusions.
Wow. Could you? No, don't shut down.
Okay.
So you went through that pretty quickly. I'm wondering if you could talk through the different PCAs a little bit more and try to interpret or try to draw out the differences that we're actually seeing and why we're seeing different.
This is the biggest one. This is a magnesium, this is silicon, and this is a CR203. That found that his previous advisor is currently looking at this part and then see why this one is an important factor of the diamond formation process, I guess.
So if we could just kind of, I guess what I'm asking is kind of for you to reflect on all that you've been talking about. Okay, the inclusions, these are different types of inclusions, right? And these
they are the chemical compositions of the minerals.
Okay, the compositions of the minerals that are inclusions. Okay, and we're seeing the different significant factors. I mean, that the principal components, and each one of these is the discovered cluster. So how do you explain the differences that we see between the different clustering algorithms, k-means versus PM? How do you explain, what's the intuition that explains why those are different? Is there any?
I think the reason why the clusters are different between them is the way that they calculate how they form. So this one is you randomly pick 13 points and then you change the points multiple times by calculating the distance, and then you finally find the clusters. So this one is you defined how many clusters you want, and then you gather the ones that has shortest distance. So that's the reason why they look different.
Okay.
So for the PCA is it's actually how much each minerals is affecting the way we cluster. So always this one is the largest on both sides.
Okay.
For the geoscience aspect, I don't really understand why they are showing the trend, but from the data science part, I would say that if we want to do 3D plots, we probably should choose these minerals as the most important ones. So these are just actually the first step of future either visualizations or machine learning methods. So this is the foundation.
Okay.
I think I know the answer to my question already, but were you able, or did you include any information in any of the analysis about mineral assemblages, mineral families? This is a igneous geology question.
Yeah, I guess Found can probably answer.
Researcher.
Okay. Well, you know, minerals always occur in groups, and certain minerals tend to be associated with them. And it really depends on the original composition of the metal.
Yes.
I was just wondering if that sort of exterior outside information is included in the analysis either before or at the end, like, you know, I think trying to explain what the different mineral assemblages in the drive.
We didn't input any grouping information in there. We just put each individual mineral as themselves and then do this kind of analysis. And I think you can see that some of the magnesium and iron.
Well, if I understand the introduction correctly, though, this data is from lots of different sources.
Yes.
And presumably from lots of different physical locations.
Yes. 5 different Cratons and the different mining locations.
But did you do any analysis on individual Cratons in isolation?
We don't really have the information on the Craton. So basically what we have is only the numbers. We don't have metadata on the
They only have
location.
what's in the paper. If the paper did any analysis, that would be.
So I was just thinking, you've got some data from Craton A.
Yeah.
Do that separately. And Craton B, do that separately, and you'll see obviously different mineral percentages. Do they make sense at all in terms of what you would expect from English college?
Probably future work is really good.
I think this
At
is
some point, you have to tie the loop with that.
Oh, sure. At this point, what they're doing is a rescue project, pulling all of these data sets out of print
It's getting the data.
and getting it into the computer so they can do this pattern. So that's definitely something.
Because, the results you have here from your cluster analysis,
Yeah,
it certainly
I think
seems like a
this
great
is,
starting point.
I think this
and of course they make sense because they are, when they are coming out from the Craton, you know where they are from, and you can usually they have some temperature information. So geochemically they do make sense, but we haven't really compared between different Cratons. Yeah.
Anybody want that project?
okay, so previously, when we did the cluster analysis, we found out that Cratons and minerals and chemical composition are not strongly correlated. That's why we did the classification on the Craton labels, and then see if any combination of the chemical compositions are correlated with Craton. And the results is like 70%, I think almost 70%. So they might mean something and they might not mean something. So this is just a result we got from numerically speaking that chemical compositions are somehow related to Craton. But generally speaking, in geoscience, they believe they're not.
So you didn't see any distinct mineral signature. They all seem to be roughly the same.
Also, this is a very small part of
So that actually leads me to another question. Typically this when this data rescue has been going on, you're viewing for the first time this larger scale data set, and there's discontinuities there. There's places that are missing, and I'm just wondering if there's any hypotheses that are saying we need to now get some data from this. Are there questions emerging? Are there hypotheses emerging from the scientists that are from the rescued data and the early analysis that said we need to get more data in this area? Do you understand what I'm asking? And that's kind of for.
Yeah. The thing is, the distribution of diamonds are really extremely biased. So they are only, I don't remember the exact number, but there are limited amount of places you can find diamonds. So it's really hard to say we won't find diamonds, like let's say in New York State. Maybe we can never find any because of the geologic setting of New York State is not a place for diamond for the kimberlite magma which carries diamonds to the surface. So
that's the source of your bias because kimberlite pipes got a very specific pressure temperature fluid material composition. There's not a lot of, you get out of the range and it just doesn't happen.
Although Fifth Avenue is a good place to find out.
Yeah. I see what she did there. So I had another data rescue question regarding that. So that workflow has been, developed. It's been evolving for quite a while. I remember when Howell was first starting on it, and he had suffered a lot of pain. So I'm wondering how, and you mentioned it's still a lot of work. It's still very hard, but I'm wondering what works really well and what are the real problems
Okay, so
that remain.
First of all, some of the papers are not mentioned machine readable, not even human.
They're ancient.
Yeah, they are just scanned and they're blur and they're not complete at all. So these are the ones that probably we will think another way of doing with it.
Mm-hmm.
And the improvement from previous, the first one is we can now extract all the tables out of PDFs successfully with the tools I mentioned. And also I look at the other, I think I mentioned that on a research group meeting. I look at another research group's work. It's called Deep Dive. It's rescuing data from PDFs. I don't know how ancient their PDFs is, but they're doing it automatically and they can put it into a Corba. So they can be used, mostly they're rescuing the text, so they're aiming for the NLP tasks. But they also do tables and numbers as well. So that's another thing worth looking at it.
But that's been a question for forever, and those you get that scanned paper from 1932. Or several of them.
A quick question about the tool you used to extract the tables from the PDFs. You said it was written in Scala?
Yeah.
PDF something it was called?
PDF figure 2.0.
Did you find a Python implementation? Is it
But
reliable?
you can just use it directly from terminal, so you don't have to,
So you can do it in batch.
Yeah, you don't have to understand.
Python's not going to save her. But did you try the R version?
The reason I ask is because we had this workflow of data rescue for quite a while, and this is a new workflow. I was just wondering if there could be continuity among we're doing the same thing.
Well, I've assumed it was evolved. I mean,
I think
In practice,
we wrote a batch script that can do all the papers at once.
so it's the same methodology, but new tools or new code.
I would hope so, because that was done a long time ago.
Before you.
For this project, no.
So yeah, that was another question was how is it being drawn together? Is it being made available? I know you said it was being made available through the data portal, but is it just being made available as a big CSV or spreadsheet? How's that?
We plan to, the goal is to make it into a database that people can query the database.
So it's not being like thrown into the knowledge graph or anything like that. That's the goal is to make it.
I haven't decided on that.
So do you have a way to evaluate how accurately you're rescuing the data?
Yeah,
Have you ever
by
checked
human.
your PDF file and the extracted data if they actually do you
We,
even have a way to
that's
check
where the human efforts kick in. We don't have other,
Even though it has not even 85% of accuracy, we still have just ask how they can see
And the best person to get an OCR to get 100% reliability is a whole lot. Pain and
All right, then.
another project.
So here's a question that's been asked from the beginning, and Howard was probably the first person to ask this question, I think, is it still more cost effective to try to do this than just to ship it off and do what is it called, the Turk?
Oh,
Mechanical Turk. I mean, if we're talking about like 570 rows and 32 columns, of total accumulated mineral data from this corpus, is it I'm and that's not to say this isn't amazing work, but I'm asking.
It's not a flat copy from here to here. It's applying some intelligence to the context of the data you get from the paper and putting it in a database in a way that it makes sense with all of the other data and measurement. How does that relate to the old one? So you could probably do mechanical Turk, but it would have to be PhD geologists doing it. So you still have to.
There are 12-year-old PhD geologists,
Undergrad.
Oh, yeah.
And this.
But we don't want to scare them.
Well, I mean, so my question was basically, when you look at the scale of this data, how does it balance? And you consider the rework and stuff like that.
We have this in this one data point. We'll let you know if there's ever another data point.
Well, but it's more than that, though. I mean, but how must have started like 4 years ago or something when you were first doing it?
Yeah, it's on
No, but the different data sets, same approach. I mean, fundamentally, you're still looking at crappy mineral, tables about mineral properties, and you're trying to have smart.
So we solved the mineralogists.
There's been probably 3 or 4 data points over 10 years, one of which I attended was found in FeiFei a couple of months ago, and it still requires an element of human intelligence that we cannot mechanize. You can mechanize or write code to select papers. You can write code to isolate the table from the paper. You can write code to delineate all the rows and columns in paper, the collection papers. But when it comes down to it, you can't really mechanize placing the data into this new format.
Yeah. And that whole contextualization that you mentioned, it's that stuff that's in the paper that's associated. That's the huge one.
Right. Especially if you run into something like this, table that's referenced by somebody else, that's referenced by somebody else, that's referenced by somebody else, and you've got to figure out then, is this useful in the context of the data I'm rescuing, or is it wrong?
Yeah.
Once the chain is custody, what's the problem? All sorts of things. So, and then you've got different instruments, different measurements, different error bars, different uncertainties, so many different things that unfortunately it requires humans still to do this.
So there's
Now,
another.
what I would love to see though, John, is in 20 years, when the majority of these papers are in electronic format, whether it is possible to up that percentage of machine help, machine work.
So kind of related to that, what I was going to say is that, so these papers accumulated over, decades and decades, the last century, they together represent the database that these scientists have used. They've not had this access, this ability to query, so to speak. Their querying has been, what do they know, and flipping through and what can they find, and the real amazing power of the data rescue effort is being able to as each thing is published, this data goes in, and it grows this larger scale database. Both sort of virtually, they can pull it down, but also potentially for real, it's a real accessible. And so my question ultimately is, how do we actually envision, how long will it take before the earth scientists are more agile at being data scientists and actually accessing that, in the way that most of us are accustomed to, of directly hammering the larger scale databases?
Yeah, I'd argue that some subdisciplines of earth science are already there.
Mm-hmm.
especially the ones that deal with satellite data.
Yeah.
Dealing with field data. Not quite.
But related to that though, that point though is that data going direct into this corpus rather than having to go into the paper, get sucked out of the sucked out of the PhD, sucked out of the PDF. Both really. Both. but I think you see the point is that it's being deposited and it's instantly growing that.
These are some of the things we talk about in like data out there with for capabilities for the data.
Yeah, yeah. Is that what Peter's over in Germany talking about right now?
Peter and Mark both. And we worry about this.
Right. So any other questions for FeiFei? This is great work. Thank you very much. Is that a question? Did you have a question or are you just holding? I thought you were.
No, I thought Beto had a question.